Welcome to Lecture 8A entitled Small Signal Modeling Framework. This material comes from Reading Assignment 2, the Introduction, and Section 3.1. The objectives here are to introduce the framework for determining the time evolution of a dynamic system consisting of state variables, inputs and outputs for small perturbations about a DC equilibrium, or sometimes called operating point. The concepts and definitions developed throughout this particular teaching module include the Jacobian matrix, what we mean by system equations, which are comprised of state space equations and output equations. And then these equations themselves consist of state variables, input variables, and output variables. Again, the notion of what we mean by equilibrium or steady state or DC operating point. Points in the case that we're dealing with nonlinear systems, in which case there might be multiple equilibrium points or none at all. And then finally, what we mean by small signal equations. All right, as usual, the second slide basically just details the contents of this lecture. So we'll just move on from here and carry on. All right, so this is the first instance now that we will basically expose you to a new definition, and that is that of a Jacobian matrix, which plays a very important role in many branches of mathematics, and we'll see this Jacobian be used in a number of contexts throughout the remainder of the term. What it does is it relates the partial derivatives of the old variables with respect to new variables, which means we're dealing with transforming from one set of variables to a new set of variables. And the three examples shown here correspond to the case where in one situation we're basically just dealing with single variable case. The second case is two variables, and the third case is three variables. So in the first case, basically what we're saying is that we're going to let x be some new function of u. And in this case, the Jacobian matrix would be just the derivative of f with respect to u. And this is a scalar, all right, because this is just a scalar equation. On the other hand, if we have, for instance, two variables, x and y, we want to express them in terms of two new variables, that's u and v. Then in this case, the Jacobian matrix is defined by taking the partial derivatives of f with respect to u and v and forming the first row of a 2 by 2 matrix, and then taking the derivative of g with respect to u and v and creating the second row of a matrix. So if we write it in this form, this is equivalent to writing it this form or this form, and we essentially say this is a 2 by 2 Jacobian matrix. Thirdly, for instance, we could have three variables. So for instance, x, y, and z each being their function of u, v, and w, u and v and w being the new variables. In this case, if we want to create a Jacobian matrix, we'd be taking the derivative of f with respect to u, v, and w, and that constitutes the first row of a 3 by 3 matrix. Similarly, we would do the same with the function g, that's a partial derivative with respect to u, v, and w, produce the second row of a 3 by 3 matrix. And the final row would be basically the partial derivatives of h with respect to u, v, and w. Of course, we can write it this way or this way or this way. In any case, this would be a 3 by 3 Jacobian matrix. All right, so let's look at some examples or problems in which Jacobian matrices appear. So let's take one example, which is, for instance, the issue of solving nonlinear equations. And this is covered in Section 1 of Reading Assignment 2. You're, of course, not responsible for this, but I'm putting it here nevertheless because in future years, if you need to do the calculation of the roots of nonlinear equations, then this is essentially the route that's typically taken. And in this case, the Jacobian matrix J is used in a recursive algorithm to compute the solution or solutions to a multivariable nonlinear set of equations. This is also referred to as the multivariable Newton-Raphson method. So for example, consider two implicit nonlinear equations in two variables. So this is one implicit equation and this another. And we essentially set them to, they're set to 0. And the objective is basically to compute what is the value x1, x2 that satisfies both of these equations. And they could in general be nonlinear equations. So in this case, what we need to do is to solve this particular equation set recursively. So x is essentially a vector which constitutes the value of x1 and x2, and x0 constitutes another vector which is more or less referring to an initial guess as to what the solution for these equations would be. That is, what is the value of x1 considered as uppercase x1? What is the value of x2? It's uppercase x with respect to 2. And so what we're saying is that if we take the Jacobian matrix and we evaluate the partial derivatives at the old values of x1 and x2, which is x1, x2, right? And then take its inverse, and then basically take this particular expression, right? Multiply through by a column vector, which involves the original values of the implicit equation f1 and f2 evaluated at the original values of x1, x2, and subtract this from the original values that we had for x0, which are x1, x2. This difference produces a new value of x, and this new value of x would then become the value that gets substituted in for the next cycle of the recursion. And you keep doing this until the difference between what is calculated and what you started with in the first place becomes vanishingly small, at which point you would declare that you have found the solution to the two implicit equations. That is, you've determined the equivalent value of x1 and x2, given an uppercase x1 and x2 respectively. All right, so we're not going to be dealing with this, but this is sort of an example of how the Jacobian matrix is used in solving the solutions to nonlinear equations. What we will be doing, though, is looking at the notion of small signal modeling, which is covered in section 2 of reading assignment 2 short. And here we're going to end up with Jacobian matrix for them. And these are used to relate small signals to each other. And these equations take on the following form. So here you see, for instance, a differential equation, a derivative of a value x1 hat, which is a small signal, and dx2 d hat dt is another small signal. And we're relating these derivatives to the original signals plus input signals. And then we have this matrix preceding this column vector here and column vector here. We also have an output equation involving y1 hat and y2 hat, which are small signals. And they are related to the source signals for the state variables x1, x2, and also the u1, u2, and u2. We call them state variables, and we call these input variables. We call these output variables. All right, so let's carry on. Here's another example in which Jacobian matrices appear. And this is something you'll find in section 3 of reading assignment 2. This is, of course, something you're not responsible for, but we're just putting it here so you understand the motivation for the use of Jacobian matrices. Now, in this case, if we were to take the determinant of a square Jacobian matrix, we're only going to be dealing with square matrices. You'll find that this is used to determine a scaling factor when transforming a differential length, an area, or a volume element from Cartesian coordinates into another coordinate system. And so this we'll be using this later when we, for instance, doing integrations, double integrations, triple integrations in other coordinate systems. Then we're going to need to compute the determinant of a Jacobian matrix. So let's look at some examples. So if it's a single variable case, x is a function of u. What has this done? It's used to map a point on the line u to a point on the line x. This is what the purpose of this transformation would be. In this case, the Jacobian matrix, as we've seen earlier, is just going to be derivative of f with respect to u, and this turns out to be a scalar. So this Jacobian matrix is a 1-by-1 matrix, which is equivalent to that of a scalar. On the other hand, if we have a two-variable system where x and y are both functions u and v, this would be used to map an area in the uv plane to an area in the xy plane. In this case, the Jacobian matrix would take this form, and we would end up basically taking the determinant of this matrix, and that will be the scaling factor that allows us to compute the area in another coordinate system. We can also go one step further. We can say, for instance, let's say we have an x, y, and z, and x is a function u of v, y is a function u of v, but h is a function of x and y. That z is h and x and y. This would basically be describing the equation of a surface. Since x is a function u of v and y is a function of u of v, then z would be a function of u and v as well. And so this type of expression would be used to map an area in the uv plane, which is planar, to an oriented area in 3D space, which is a curved surface in 3D. In this case, friends, we could set up a Jacobian matrix of this form. It looks a little bit different. These x, y, hat, z would be basically the unit vectors in Cartesian coordinate system. These are the partial derivatives with respect to u and v. And if we were to take the term of this matrix, this would essentially allow us to compute differential surface area element on the surface of a curved surface. We'll be dealing with this later in the course, in particular in lectures 19 and 20. And finally, we have, for instance, x, y, and z being functions u, v, and w. In this case, this will be used to map a volume in u, v, w space to x, y, z space. If we then take the Jacobian matrix, it would be a 3 by 3 matrix. And if we take its determinant, then we'll find that being a scalar is in fact the scaling factor that allows us to compute the volume of an object in another coordinate system. And lastly, the transformation of coordinates for vector operators. We are not going to deal with this topic, but nevertheless, it's covered in Section 4 Reading Assignment 2. And we'll be dealing with this later in the course, these new operators, but we just suffice to say for now, let's see what these actually represent. So the Jacobian matrix is used in the derivation of vector operators in coordinate systems other than Cartesian. And the ones that we'll be discussing in this course are the gradient operator, which operates on a scalar function f to produce a vector. We're already aware of this particular operator. The divergence operator, which again has the same symbol with a dot. It's a dot product operation that operates on a vector to produce a scalar function. And lastly, we have the curl operator, which is again this operator, and this sort of multiplication sign, which is essentially like a cross product. Well, this would operate on a vector to produce a new vector, which takes on this form. We'll be discussing both of these later in the course. All right, so now we introduce a small signal framework, and we start with what we call system equations. And so what I've shown here is sort of like a box, and these x1s and x2s to xn refer to what we call state variables. We'll talk a little bit more about them. These represent the internal state of the system, such as a current through our voltage across an energy storage component. So for instance, if we talk about a capacitor, we will associate the capacitor voltage with the state variable. If we're talking about the inductor, we're going to associate the current through the inductor with the state variable. So you'll be putting inputs in. These inputs basically will interact with the system, which is described in terms of differential equations, and there might be a number of outputs. Here I've made it quite generic. I said there could be as many as m inputs, could be as many as k outputs, and there could be as many as n state variables. So let's take a specific example of two state space equations, which involve two state variables and two input variables, and output equations involving two state variables and two input variables. So notice here, for instance, the fact that I have a derivative on this side of a state variable, basically completely isolated, this being a function of the state variables and the input variables. And similarly, we have another derivative equation, a derivative with respect to the second state variable x of 2, and this also is some function of the state variables and the input variables. This descriptor that you see here, or this sort of set of expressions, we call state space equations. And these x1 and x2s are internal variables. The output equation would have this form. y1 would be a function of the state variables and input variables, and the second output in this case would also be a function of the input variables, the state variables and the input variables. All right, so just as a reminder, when developing state space equation to model system, you only want one derivative to appear in each state space equation. All right, so here are two state space equations that we're dealing with here. All right, so let's take some examples in terms of system equations example. I've got a circuit on the right, which basically is a typical RC circuit. This Vn is some voltage source. It doesn't have to be DC. It's quite generic. And the problem statement is derive the system equations for this circuit, assuming that the output variable is the power loss in the resistor, that's across here, and the input variable is the voltage source Vn as a function of time. So this is varying as a function of time. And so the solution process in this case would be to write out a loop equation, which means you apply Kirchhoff's voltage law around the loop, but you also realize that the current through the capacitor is related to the voltage across the capacitor through this relationship here. Notice this v of c appears in the derivative, and therefore v of c is a state variable for this particular circuit. There's only one energy storage component in the system, so there'll be only one state space equation. So the second step would be to write the loop equation in standard state space form, which means on the left side there can only be a single derivative expression and no scalar multiple. And finally, step 3 is to write the output equation in terms of the state variable and the input variable. So the state variable we're just going to say is v of c, but we're going to call it x01. Input is v n of t, but we're going to call it u of 1. The output variable is p of n, but we're going to call it y1 just to be consistent with the nomenclature we used on the previous slide. So let's basically go through each one of these steps in turn to see what we end up with. So step 1 would be to write out the loop equation. So the loop equation, this is the current through the capacitor. That's the same current flowing through the resistor. The resistance times the current is the voltage drop appearing across the resistor, which is the net difference voltage of Vn minus Vc, which you see here. So this is step 1. This is essentially Kirchhoff's voltage law being applied to this circuit. However, this is not in state space form. We need to divide through by RC on both sides, which allows us to obtain an expression of this form. And so this would be 1 over RC V of nt minus 1 over RC of V of c. This is also going to be a function of time. And you can see that this function is a function of the state variable, V of c of t, as well as the input variable, consistent with the description that we gave for the system equation on the previous slide. All right, what about the output equation? Well, the output equation would be the power loss in the resistor, which is basically the square of the voltage across the resistor divided by its resistance. Well, the square of the voltage is the difference between these two voltages squared, Vn minus Vc squared over R. But notice here that the output equation is also a function of a state variable, which is V of c, and the input, which is V of n. So more or less that's the equations that we would have, and it's these equations that we're interested in looking at in terms of developing a small signal model, which means if we make small changes in the input voltage, how will that affect the power across the resistor? All right, so this is just a quick review. System equations for a linear system. If I have a matrix, an n by n matrix, by a column vector with n entries, you obtain a new column vector with 2 entries. So for example, here, if I have a matrix of this form, times x1, x2, then effectively the way you go about doing the multiplications is you take this row times this vector, and that gives you this equation. You take this second row times this vector, and this gives you the second equation here. So in effect, knowing that the rules of multiplication of matrices look like this, we can start with this state space differential equation set. In this case, I said it's linear. Linear meaning that everything on the right here is a function of a linear function of the state variable or the input variable. So here, for instance, these are A1, A12 are associated with the state variables, B1s, B12s, and so on are associated with the input variables. These two equations, according to the rules I've shown up here, can be rewritten in matrix form. And so what we end up with is something much more compact. We have a matrix A consisting of 4 elements times a column vector x1, x2 plus a matrix B times a column vector involving u1 and u2. And of course this would be A and this here would be B. Output equations could have a similar form shown here. We can basically relate these to a matrix equation as shown here on the right. Here's the matrix involving the state variables, and here's the matrix involving the input variables. And of course these 4 elements constitute the matrix C, and these 4 elements here constitute the matrix D. All right, what about a nonlinear equation? So for example, if we look at these set of state space equations, you immediately realize that this involves the square of a state variable, which means this is a nonlinear equation. When we're dealing with nonlinear equations, we basically cannot work with matrix equations. It has no meaning because matrices are applied to linear systems. In this case, the second one is a linear equation. What about the output equations? Well, the first output equation is linear in x1, x2, u1, ut. Unfortunately, it's nonlinear in the second equation, y2, because of u2. It's u2 to the power of the 4th. So again, we cannot write this in the form of a matrix equation because we are dealing with a nonlinearity here. All right, so now let's look at the evolution in terms of how do we go about creating a small signal model for these set of system equations. So first thing we want to do is to perturb the input signals, which means u1 of t becomes u of 1, which is whatever the static value is. And this is the perturbation of that signal. U of 2 will have its static value, and of course you will perturb it as well. And these are what we call input operating points. U12 and U2t are small input signal perturbations as a function of time about the input operating points U1, 2, and U2 respectively. All right, so that deals with the inputs. We also have to perturb the state variables and the output variables. So that means x1t becomes x1 uppercase plus small signal variation of x1, similarly for x2, similarly for y1, and similarly for y2. So these x1 and x2 are referred to as the state variable operating points, and y1 and y2 are referred to as the output variable operating points. So we essentially have outputs variations, we have state variable variations, and input variations. So that's the starting point. All right, so the next step basically is to substitute the perturbed signal expressions into the original differential equations and output equations. All right, so what we've done is replaced x1 by x1 plus x1 hat. But if you take the derivative of this, x1 being a constant, you're just left with the derivative of the small signal with respect to t. And on the right-hand side, essentially all we've done is replaced x1, x2, u1, u2 by the steady state or equilibrium value and a perturbation, and that's the case for each one of these four. You do the same thing for the second state space equation. The x2 being a constant means that you only end up with the derivative of the small signal perturbation, that is x subscript 2. For the output equation, we do similarly the same thing. We have y1 plus y12, y2 plus y2 hat t, and then the x1, x2, u1, and u2 get replaced by the expressions that you see here. So what we're going to do now is we're going to approximate the functions on the right, that is for the differential equations and its output equations. We're going to basically approximate them by a Taylor series to first order, which means we keep basically the first order term, which will be a constant term, and the second next term would be basically involving first order derivatives. And if the signals u1, u2, x1, x2 are small enough with respect to the operating points, then we can essentially say that the Taylor series expanded to first order is sufficiently accurate, and we don't basically have to worry about second and higher order terms. All right, so here basically we're just showing the first order expansion, and so there's the first order term, and then of course we have x1, x2, u1, and u2, and so you can see perturbations with respect to the input variables and perturbations with respect to the state variables, both for x1 and x2. And so this represents the operating point. This is changes in u and changes in x. And you'll notice that once you take a partial derivative, you hold everything constant except the variable that's being you're taking the derivative with respect to. But once you've taken the derivative, then u2 is replaced by its steady state value or equilibrium value, which is u of 2. And this is done essentially for all of the partial derivatives that have to be computed here. All right, what about the output equations? Well, very similar. Essentially, what we're going to do is expand this function to first order. And so there's an operating point. There's y1 plus y hat. This is the operating point, changes of x, and these are the changes with respect to u. Now, of course, we could graph various things. You look, for instance, how does the output change for y1 or y2 with respect to changes in u1 and u2 or x1 and x2. And so this is just showing, say, for one combination with everything else being held constant, and you would have a graph similar to what we had discussed in a previous lecture. And so what you're doing is you're just making a small signal perturbation in the input. That input could have been a u, it could have been an x, and you're looking at the corresponding change in the output, which could have been a y1 or a y2. So same idea as before. And again, we're approximating basic things by a straight line. All right, so effectively this is like recycling the material from the previous lecture, but there are more combinations to consider. All right, so next step is basically the Taylor expansion to first order, but we're going to put it into matrix form. And why is that? Is because the derivative terms involve linear perturbations. So u1 is linear, u2 is linear, x1 and x2 are all both linear. So all of this can be represented in matrix form, as I've shown here. So a 2 by 2 matrix associated with changes in the input signal, and a 2 by 2 matrix associated with changes in the state variable. And so this matrix I'm going to call B of f, B subscript f, and this matrix I'm going to call J subscript f. So it's just another way of writing it. It's just in a more compact form, but can be done. All right, output equation, same idea. You can basically group things, and because it's linear and u1, u2, x1, x2 hat, we can basically write this out in matrix form, and so these are two different matrices, J sub G and B sub G, right? All right, so now the procedure for developing small signal model using a 2-input, 2-state variable, 2-output variable example. So first step is to convert state variable equations into a state space form and identify the input variables, state variables, and output variables in the output equations. So one case considers a set of differential equations, output equations, which are given to you. The other possibility is a circuit diagram with input variables and output variables given, and what you need to do is, using the circuit diagram, determine the differential equations, the output equations. So this is an extra step that needs to be taken. This was an example that we had just discussed earlier in terms of first of all setting up the output equation and the state equation, but we did it for a single variable case. All right, having done that, the next step is to determine the equilibrium state variable operating points x1 and x2. It's the first step. We know what u1 and u2 are, which are the steady state values for the input variables, but we need to determine x1 and x2, because without x1, x2, we cannot determine the steady state or equilibrium points for y1 and y2. So this comes first, and then having computed x1 and x2 and knowing u1, u2, we can compute y1 and y2. Having done that, we can compute the Jacobian matrices, the 4 of them. Why? Because we have all the steady state points, and don't forget the Jacobian matrices involve partial derivatives, which are evaluated at the equilibrium points. And then 4 is to write out the small signal state space equations, which have this form, and the small signal output equations, which have this form. And then we can basically look at the original equations, which involve the steady state values with the perturbations. This would be the total. And on the output side would be the original values plus the perturbations in the output variables, which is the total. All right, so here basically we now show the small signal model for the status equations. And again, we have this plus this term, and then basically the small signal AC input, which is this one here. Now this term is going to be 0. All right, we just show. So effectively this will be, I could have written this as just this is equal to this and just say it's 0, but I left it here basically because it's an extension of what was done on a previous page. So because this is 0, steady state equilibrium is when there's no changes here, no inputs, and by definition then this becomes 0, and so this term basically makes no contribution at all. And so we're left with a small signal model which has this form here, and the matrices are the ones that you see here. So the whole problem of small signal modeling will be a two-step problem. One is to solve for x1 and x2, and the second step would be to compute these Jacobian matrices, given that you've computed the equilibrium points for x1, x2, and u1 and u2 would have been given. All right, then the output equation. So same idea, that we have this. All right, but we know that the output variable equilibrium points, y1, y2, is in fact equivalent to this. So these two basically represent this combination, which means y1 hat, y2 hat is everything you'd see on the far right. So the small signal output equations will take on this form. And again, you can compute what these Jacobian matrices are. Once you've established what the equilibrium values for x1, x2 are, u1 and u2 will have been given. So that more or less basically takes you through the whole process. All right, so the last thing we want to talk about is why is small signal modeling employed? And in the notes we go in a little bit more detail, but I just want to give you an example of something that you'll be exposed to next semester in EC 231, which is the microelectronics course. So what I'm showing on the right here is a transistor circuit, which is an amplifier. And so we have a voltage that goes into this variable resistance. I have an output voltage, and I have a resistor connected to this transistor. And so what we're going to do is adjust this value of resistance to adjust the amount of current that's flowing into the transistor. That this IB here refers to the IB that you see for these individual blue curves. So if you set this for a specific value of resistance, you're setting yourself to be on one of these blue lines. All right, so the next thing would be to figure out what happens if I raise the collector emitter voltage. That is, if this voltage goes up, how does that impact the current that's flowing through it? Well, for a transistor, you basically will see this relationship for a given current that's flowing here. You can see how that changes. So for instance, if IB were 60 microamps, this value would have adjusted to produce 60 microamps. Then you can see that as the collector emitter voltage increases, then the current that flows through the transistor is basically following this blue line. All right, so that basically is the operating characteristics of the transistor. At the same time, we can write an equation using Kirchhoff's voltage law, which is that this voltage minus the voltage drop across this resistor minus the collector emitter voltage equals 0. And if we do that, we end up basically with the straight line that you see here. So this is what we call a load line. This is a load line. So this is the current. Basically, it's been written in as function of collector emitter voltage. What is the current? And so this is the line you've got. The intersection between this line and the particular blue curve you happen to be working on turns out to be the operating point. So the operating point, when we're dealing with a base current of 60 microamps, would be a collector emitter voltage, which is approximately 12 volt, and a current that's flowing through the transistor that's approximately 5 milliamps. All right, and so what we're going to then do is we're going to make small changes in this resistance value. What will that do? That's going to make small changes in the current that's flowing through here. Small changes of current flowing through here is equivalent to saying we're moving from this blue curve to a different blue curve, up and down, up and down. Now the details that are not shown on this graph, this is basically dealt with in the lecture notes in more detail, but I just illustrate basically how you would take this diagram and make some sense out of it. All right, why we do all this? Well, we want to investigate the stability of a physical model about an operating point, and then design a controller that delivers robust regulation, fast response without oscillations, and good tracking performance. That is, you request a certain signal and you want to make sure you actually attain that signal with minimum error. And so this more or less essentially is the motivation as to why we do small signal modeling. Of course, there are other applications out there in which small signal model is employed. That concludes Lecture A. Thank you for listening.